Lesson number 26, daily summary. In this lesson, we solve word problems that involve maximizing or minimizing a quadratic equation. Number 1, have a look at graph A, whose equation is y equals x squared plus 5x minus 6. Using the graph, write the coordinates of the x-intercepts. Okay, so we can read the x-intercepts off of the graph. Looks like at negative 6 and positive 1, but we want coordinates. So that means we're writing the y values as well, and if we're on the x-axis, then the y values are 0. So those are the coordinates of the x-intercepts. Let's find the x-intercept of the vertex by doing something to the answers we got in part A. Well, what are we supposed to do? Well, we're supposed to average, right? That's how we find the x-coordinate of the vertex. So we'll say averaging. I think that's how you spell it. I don't know about that E in the middle there. What are we thinking? Averaging. That looks worse. Okay, so we're going to average the x-coordinates of the x-intercepts. So here we go. To average two numbers, I add them up and divide by 2. My x-intercepts, just the x-coordinates, are negative 6 and 1. That's negative 5 over 2. Negative 2.5 is the x-coordinate of the vertex. Notice the little subscript v. And does that jive with the picture? Is the x-coordinate of this vertex around negative 2.5? Well, yeah, it sure looks like it. Negative 2.5, smack dab in the middle of my x-intercepts. Turns out there's an easy formula to find the x-coordinate of the vertex of any parabola, easier than locating the x-intercepts and then averaging them. Mind you, finding x-intercepts is usually a harder task than we had. We got lucky because we had the picture in front of us, and so we could just read them off. But if you wanted to actually find the x-intercepts from the equation, we would change the y into a 0 and solve that equation by either factoring with the 2x2 box or using the quadratic formula, both of which are, kind of involved processes. So we can skip all of that if we learn this magic new formula. Here we go. For the quadratic equation, y equals ax squared plus bx plus c, the x-coordinate of the vertex is given by the formula, the vertex formula, x sub v equals negative b over 2a. Negative b over 2a. Let's check this out. So A, B, and C are the same things that we've seen before many times now. A is 1, B is 5, and C is negative 6. Okay, so negative B over 2A. So how much is B? Okay, it's up there. It's 5 divided by 2 times A. That's 2 times 1. So this is really negative 5 over 2, which is, oh my goodness, negative 2.5. The same answer that we got before. But in a whole heck of a lot easier way. Here we had to find two x-intercepts, which is supposed to be harder than it was, but we got lucky with having the graph in front of us. And then we average them. But look, all we have to do is this snazzy little formula. The x-coordinate of the vertex is negative b divided by 2a, and we've got it. And the nice thing about that snazzy formula is that you've seen it before. In fact, it's part of the quadratic formula, right? Negative b plus or minus a big old square root divided by 2a. But do you see the negative b over 2a inside of there? I hope so. And more than just seeing it right here, I'm going to continue to circle the x. It's even part of the quadratic formula that this is specifically an x value. It's not just a fraction floating. X equals negative b over 2a. That's it. So that's how we find the x-coordinate. Now finding the y-coordinate, there's no shortcut there. Actually, there is a shortcut, but I'm not going to tell you what it is. But I'll just say there's no shortcut there. Finding the y-coordinate involves taking the x that we just found, negative 2.5, and plugging it in right here and right here for every single x, and then doing the arithmetic, and then whatever you get is the value of y. So here we go. You take your original quadratic equation right there, and we're just going to change both x's to negative 2.5, and then we do arithmetic, maybe with the help of a calculator. Negative 2.5 squared becomes positive 6.25. This multiplication turns out to be negative 12.5, and then the minus 6 is just copied there, and we smush all that together, and we get negative 12.25. That is the y-coordinate of the vertex. So that means that both coordinates of the vertex are negative 2.5 and then negative 12.25. And you can check the graph and make sure that you agree that that jives with the picture. So in this particular case, is the vertex that we found above the maximum point or the minimum point of this parabola? Well, that parabola opens upward. I know because I'm looking at the picture, but I should also know because the value of a in this case is positive 1. And if a is positive, the parabola opens up. And if your parabola opens up, then the vertex is the lowest point on the graph, right? It is the minimum of the graph. So our particular vertex, this -2.5, -12.5, is the minimum. But if you were looking at the vertex of a downwards opening parabola, then the vertex would be the highest point, would be the maximum possible value of y. So our vertex is a min because our parabola opens up. It is often useful to be able to determine the smallest and largest value a quantity can assume. For example, companies try to minimize costs or maximize profits. If you see the word maximum or minimum or biggest or smallest or highest or lowest or any synonyms for any of those words, if you see one of those words in a word problem, there is a very good chance that the answer is the vertex. So if your teacher gives you like a test or a quiz, they probably aren't going to say, hey, here's the equation of a parabola, find the vertex. They might say, hey, here's a word problem, and here's an equation. Find the maximum, or find the minimum, or find the least, or find the biggest, or any synonym for those words. And you immediately translate any of those individual words to, oh, this is my teacher just asking me to find the vertex. And then you use your spiffy new vertex formula, x equals -b over 2a. We began graphing parabolas a couple of classes ago. Now that we have an easy way to find the vertex and one that works even when there are no x-intercepts, we can graph certain kinds of parabolas that we couldn't before. Every parabola that you graphed a few classes ago had some x-intercepts because we didn't know how to do anything when the graph didn't have x-intercepts. But now that we can find the vertex without x-intercepts, we can graph a larger class of parabolas. Here's a new and improved 6-step process to graph parabolas. I'm going to highlight the things that are the same and then the things that are different. Step 1, figure out if the parabola opens up or down. That's the same. Step 2, it will go green for the same. So you just go ahead, green means go, do exactly what you did before when we graphed parabolas a few classes ago. Step 2 is the same, find the y-intercept by setting x equal to 0. Step 3 is different, so we're going to slow down, yellow for slow down, right here. Let me tell you, the old step 3 was to find the x-intercepts, and that means changing the y equal to 0, and that means either quadratic formula or factoring, and either of those is an involved process, as we've seen. And we couldn't before graph any parabola that didn't have any x-intercepts because we couldn't find the vertex. But now we can. And so we're not going to find the x-intercepts because there might not be any. So why waste our time finding these x-intercepts if they might not even exist in the first place? So instead, our new step 3 is to find the axis of symmetry and also the x-coordinate of the vertex of the parabola. These both can be found with the formula x sub v equals -b over 2a. So we just saw that formula for the x-coordinate of the vertex. Once we know the x-coordinate, we plug it into the original equation to find the y-coordinate of the vertex. All right, based on our answers to steps 1 and 3, we're supposed to determine if there are 0, 1, or 2 x-intercepts. I'm not going to read those cases just yet, but let's suppose that you have a parabola that opens down, and you can tell that right away by looking at the value of a. And suppose that you do this new vertex thing in step 3, and you find that the vertex is right here. So the question is, if you have a downward parabola and it hits the vertex right there, how many x-intercepts will we have? Well, I think that should be easy. Just draw yourself or imagine a parabola opening down and hitting that point as its vertex. You're definitely going to have 2 x-intercepts, right? One here, one here. Now, I don't know, I couldn't have drawn it as accurately as I did. Like it could have been like really thin or it could have been even wider than it was. But no matter what, it's going to have 2 x-intercepts. So then you find the 2 x-intercepts and using the old processes, the factoring or the quadratic formula. But what if I change this and I say that now this parabola opens up, but the vertex is still right where I've drawn it. Now how many x-intercepts will it have? Well, this is quite a bit different. If it opens up and it has that vertex, it has no x-intercepts. So don't bother wasting a moment trying to find them with factoring or the quadratic formula. It doesn't have any. And so we find the vertex first, and then we decide whether or not we should even bother looking for x-intercepts based on where the vertex is located and whether the parabola opens up or down. And if it doesn't have any x-intercepts, well, we still need a few more points. You can't just plot, like you'd have the y-intercept already, and then the vertex, and then the symmetric point for the y, intercept. You just pick another point, like if, x equals 3 is near the action, you find out, plug x equals 3 into the original to find the y value. And then there's, of course, the symmetric point to the 3. And then you've got your 5 points and you can plot them. But no need to look for x-intercepts when there aren't any. All right, suppose now that I've got a parabola opening upwards, but in this case, the vertex happens to be here. How many x-intercepts will this one have? Well, if it opens up now, it's got to have 2. A second ago, it had none because the vertex was above the x-axis, but now it has 2 x-intercepts, there and there. So we should find them. Suppose now we keep it opening up, but now I'm going to put the vertex right on the x-axis. Suppose that this is the vertex, and it opens up. Now how many x-intercepts will we have? Well, this is a special case. It's just going to barely graze the x-axis and run away. It's going to have only 1 x-intercept. Should you spend time finding it? No, you found it already. It's the vertex. So don't spend any time looking for other x-intercepts. There aren't any. Okay, so I think that's good. Just have to reason your way through based on where the vertex is and whether the parabola opens up or down. And so you can read the cases here in step 4. It's in bold, but hopefully those cases make sense based on the description we just made. Okay, step 5, same as before. I don't know if it's in the same location as before, but step 5 is a green one. Yellow one is brand new for us. Step 5, find the coordinates of the point across the axis of symmetry that is symmetric to the y-intercept. Step 6, plot all the points you found above and sketch the parabola with a smooth continuous curve. That is old. Give that one a green. But if the points you found are very close to each other, you may have to plug in another value of x of your choosing to get another point. Remember, anytime you get one point, you can fairly easily find its mate that is symmetric to it across the axis of symmetry. In fact, you might just need to plug in random other values of x because you don't have enough points to plot because there were no x-intercepts. Okay, so let's do just the beginning of this one, and you can finish it as the start of the activity. It says, consider the parabola with this equation, y equals 4 plus 2x minus 3x squared. We'll find the coordinates of the vertex and the x-intercepts if there are any rounded to the nearest hundredth. You should do the rest of the six-step process later. This is a calculator active problem. Okay, here we go. I'm not thrilled with the order of the terms, so I'm going to put it in my standard order, our standard order. So x squared first, x term in the middle, constant term last, but just be faithful to the signs that were originally there. Okay, step 1, up or down? Well, let's see. A is -3, which is for sure negative, so this parabola opens down. Step 2 is to find the coordinates of the y-intercept. So if we let x equal 0, and we get lots of zeros and just the number 4, so that means that the y-intercept is 0, 4, easy enough. Okay, the old step 3 was to find the x-intercepts. Not now. Now the new step 3 is to find the vertex. So I guess we can number these, right? That's 1, here's 2, and then step 3 is the vertex. And we just use our spiffy new formula, x sub b equals negative b over 2a. Negative b, okay, so that's a negative, and then b is 2 up there. And then divided by 2 times a is -3. And so we get negative 2 over -6, which reduces to 1/3. Okay, so that is the x coordinate of the vertex, 1/3. And now we're going to find the y coordinate. I think actually this is the hardest part of this problem because we're just going to have some fraction arithmetic to do, but life goes on. So the y coordinate of the vertex involves taking the original equation up there at the top of the screen and plugging in 1/3 for all those x's. -3 times 1/3 squared plus 2 times 1/3 plus 4. Okay, we'll do the 1/3 squared, so that's 1/9, plus then 2 times 1/3, so we just multiply straight across 2 over 3 in that case, plus 4. Let's go ahead and reduce here. I see a -3 on the top and a 9 on the bottom, so I can divide both by 3. And then I can multiply straight across, so just be very careful here, but I think we just get -1/3 right there. Plus the 2/3 plus the 4. -1/3 plus 2/3, that's +1/3 plus the 4. You can write it as a an improper fraction if you wish. I'll leave it as 4 1/3 because we're about to plot this thing anyway. So 4 1/3 is good for me. And that means that the vertex itself, both coordinates, we found x first was 1/3, and then the y coordinate 4 1/3. So we can plot that one, 1/3, comma 4 1/3. So 1/3 we're just estimating, 4 1/3 we're just estimating, but somewhere around there is my vertex. And the first thing we established here was in orange, this parabola opens downward. And so I'll draw it, but then get rid of it. So this parabola hits that vertex and goes down. So then how many x-intercepts do we see? Do we expect? We expect 2. So we should find them. But it was worth a shot. It was worth checking to see if there were going to be any x-intercepts at all. So we find the x-intercepts in the traditional way. We're going to go to that blue equation at the top there and change the y to 0. So here's step 4. The y becomes 0. Everything else in the equation gets copied. And now we solve this equation for x. So you can spend some time trying to factor. Greatest common factor is 1. It's not a difference of 2 squares. You could try the 2 by 2 box. I think ultimately you will find that the 2 by 2 box is not workable. It's just this one is not factorable. And so if it's not factorable, then the only alternative is the quadratic formula. And so we do it. So let's go ahead and start plugging in. So negative, and then we had up on the top there, the value of b was 2, plus or minus, square root. B is still 2, minus 4 times negative 3 times 4. All divided by 2 times a, 2 times negative 3. So this equals negative 2 plus minus square root of 2 squared is 4, minus minus makes plus. 4 times 3 is 12, times 4 is 48, all divided by negative 6. So we get negative 2 plus minus square root of 52 divided by negative 6. So those are the x-coordinates of the 2 x-intercepts, and they're irrational numbers. We got that square root of 52 there. You're welcome to simplify this one. I guess I probably should. Ultimately, because we're trying to graph the thing, we're going to go to decimal land anyway. So we're just going to type something into the calculator, and I'm happy enough just typing this thing in the calculator in its current form, but I suppose we should reduce it as far as possible. So this is the part where we split into 2 fractions. That first fraction reduces as usual, 1/3. Plus minus 52 has a perfect square factor. It is 4. And then 4 times 13 gives us that 52. The square root of 4 comes outside as 2. The square root of 13 isn't going anywhere, divided by negative 6. So we get 1/3 plus or minus, okay, so 2 over negative 6 is really 1 over negative 3. I won't write the 1, but we have to write the negative 3. So there you go. That's the simplified version of the x-intercepts. And so we can just type them into the calculator and get decimals to plot these x-intercepts. So we'll do that real quick here. I'm actually just going to go back to this version to do the calculator bit. So I'm just going to do the numerator first, negative 2 plus the square root of 52. I will hit enter there, and then that's supposed to get divided by negative 6. And so that's one x-intercept, right around negative 0.87, we can say. And then if I do second entry twice, then I can just come over here and replace the plus with a minus. So that's the minus part of the plus minus. And then we can divide that thing by negative 6 and get our other answer. So right around negative 0.87 and 1.54. So negative 0.87 and 1.54. And these are x-intercepts, so they're points, so they got to have 2 coordinates. The y-coordinate for both is 0. And so we can estimate where these things are on the grid. So negative 0.87, so pretty close to negative 1. And then 1.54, so right around there. And you can see this is a really narrow, tight kind of parabola. And we also had the 0.04, which we didn't plot before, but we can. So that guy is very close to the vertex. And I'll just do one last piece here, the symmetric point to the y-intercept over the axis of symmetry, which is right here going through the vertex. And remember, the vertex was at x equals a third. So if I have to go from the y-intercept to that vertical line, how far do I go? Well, I go a third. And if I want to get to the symmetric point, I need to go another third. So we're just going 2/3 right here, and we're keeping the same y value as the y-intercept. So I think that's our symmetric point over the y-axis. So there you go. And then we connect the dots with a smooth, continuous curve. This is a very tall, narrow parabola. I can't do better than that. I know it's a Friday, but come on. A thing of beauty. Try it over here. Okay, good enough. So that's our parabola. Make sure your parabola extends all the way to the edges of the graph paper. And the last thing I'll say, these tiny URLs are links to YouTube pages. I haven't checked them in a while. I don't know if they will still be live links by the time you get to check them out. But if you have a few minutes, you could watch like 5 minutes of this clip right here, and then like a minute of this clip right here. Again, those just take you directly to YouTube pages. So some cool stuff happening with parabolas and weightlessness. So check it out. Hopefully the links are still working for you when you go.